Good morning, everyone. I hope everybody's doing well this morning. There's nothing better than a early math class to get the day rolling. I think when I first started teaching at San Jac, the early classes were an adjustment, but I learned that most of my students in the morning were more awake, even though that didn't seem at the time to make a lot of sense. But I'm glad everybody's here today. And what we want to do is to continue with some of the topics that we were starting to discuss at our last class. And the first thing I want you to do, again, please remember today, as I have for the last 2 days, I will be sending invitations for the Zoom conference hours. Remember, the conference hours are optional, but they are Zoom meetings where you can come and ask questions about the problems you're working or anything of that nature. So today I actually have 3 different sessions. I must have lost my mind when I was scheduling Thursday, but there will be 3 sessions today, and I will always send out email notices for that. So you'll have those in your inbox, so they'll be real easy to access. So just remember, as you're working through the week, it's like, oh, I have some questions here. Let's go to Professor Ron's conference hours. So please take advantage of that. Now, what I want to do, just to get you all warmed up, is to do a warm-up problem from your WebAssign. And actually, this is not particularly directly from the WebAssign. It's actually a problem from your textbook. Remember, when you go to your ebook, when you look at the daily schedule, you see lots of numbers. And I know some of you actually have access to a hard copy book, and that's fine. But when you actually use the ebook, all the pages are there, but in a format that's very easy to use. So if you're fortunate enough to have a loose leaf copy of the book or a hardbound version of the book, that's fine. It's certainly not required. Sometimes books get passed down to students from friends and relatives, and that's always nice. But in this day and time, we don't get free books anymore. Everything is ebook online, so to speak. Now, we talked about the square root property, and I'm going to say more about quadratic equations today and solving equations in general. But I thought this was an interesting problem. When you look at this particular example, it says solve for r sub 1. And what we have here is an equation that you would see in a physics class. That is, we have 1 over r. This would be a parallel resistance type problem. We have 1 over r is equal to 1 divided by r sub 1 plus 1 divided by r sub 2. And the problem says just solve for r sub 1. So this might be a good physics question, or it might even be a good question in a calculus class when you do optimization problems next term in Calculus 1. So what I wanted to do was just solve for R1. So first, what we can do, again, this is nothing unique about what I'm doing. I want to go ahead and isolate the term that has the R1 in it. There's only one of them. So we have 1 divided by R1. And then, of course, we can subtract this term from this term to isolate the R1 term. Now, at this point, we would like to be able to solve for R1, that is by reciprocating, and that would be the easiest way to go, but it's a little bit difficult to reciprocate these fractions when we don't have a common denominator. So the next thing we can do is get a common denominator. So again, working with numbers, letters, it's all the same thing. So we have a common denominator of r times r sub 2. And then, of course, to compensate for that, here we don't have the r sub 2. So we have 1 times r sub 2. And then of course here we don't have the r, so we have the -1 times the r. So again, when you look at this particular expression, when you break it up into two pieces, the R2 over R times R2 just gives you 1 over R, and the negative R divided by R times R2 just gives you the -1 over R2. So that's an easy way to check your work, especially when you're getting common denominators. Very simple, but like I said before, every aspect of the problem is important. We don't want to think, well, that's an easy step, I'm not going to think about that. But unfortunately, the easy steps are what always confound us. We'll make a careless mistake and not even be aware that we've done it. And now we've got a nice setup here. We have fraction equal a fraction, so we can reciprocate. So reciprocate both sides. So we'll have R1 equals, and reciprocate this, R times R sub 2 divided by R sub 2 minus R. So again, maybe not a very fascinating problem, but certainly a problem that you do in your science classes, math classes, and then of course your future engineering classes. So again, like I said before, just remember that a lot of the problems that we'll be doing in the first week are just preparation. That is, review things from college algebra, review some ideas from algebra 2, maybe things you haven't thought about often, but just to kind of get our wheels turning again so that we're thinking algebraically and that we're thinking laws of exponents and adding fractional terms, things that are actually very simple, but extremely important. Now, I had one other example that I wanted to do that utilizes the square root property with a similar problem. And then we're going to talk about solving some more equations. So in this particular example, it says solve for lowercase I. I thought these would be good examples. And in this case, the lowercase I, ladies and gentlemen, is an annual interest rate. So we're going to think of this as being a positive quantity. So this is an annual interest rate. And here's the problem. This is a compound interest formula, so I'm sure you've seen this before. We'll say more about this later on in the course when we review, but I thought this would be just a nice way to introduce it again. So we have A is equal to P times 1 plus I over 100 squared. So that's the formula that we're given. And now the reason I mentioned the fact that the annual interest rate is a positive quantity, I'll just say note, when we think of an annual interest rate, we define that to be positive. So we will just kind of think of this in the background. Now, of course, when you solve this problem, they're not making any allusion to what these variables mean. So you can actually put both selections that we'll get from the square root property. But I thought it just might be nice to push it forward one more step. For instance, if we were actually doing an interest problem. So now when we look at this and we want to solve for I, first we need to make sure that we have the squared portion isolated. So the first thing we're going to do is divide by P. So equivalently, that's why I always write the double arrow here for equivalent. We have 1 plus I over 100 quantity squared equals A divided by P. And I thought this would be good because now we have what we talked about yesterday and what you talked about in your college algebra class, the square root property. So we have something squared equals a real number. So now by the square root property, we have 1 plus I divided by 100 will now equal plus or minus the square root of A over P. Again, that's the statement of the theorem, the square root property. and very useful to us. Again, utilizing concepts about real numbers, even complex numbers. Now what we can do is see that we can actually solve for the fraction I over 100 by subtracting 1 from both sides. So we have I over 100 equals plus or minus the square root of A divided by P minus a 1. Now, this is where I reference the fact that, again, this would mean that we would select the positive radical here, because of course, if we selected the negative, we would determine that I is a quantity less than 0, and it's an annual interest rate. So this would be an example where we would definitely select the positive. I mean, we can go ahead and leave it as plus or minus since the problem's not really alluding to the types of variables. But as an extra, we can say for I positive, we select the plus radical. So for instance, if we were doing an interest problem, we would certainly want to be able to make sense out of our computation. So now this would imply, or equivalently, we have I over 100 equals the positive square root A over P minus 1. And then, of course, we can multiply by 100. I will now be 100 times the quantity square root A divided by P minus 1. And that would be a formula for the annual interest rate. So again, the power of algebra is what you've known since you started in your Algebra 1 class, probably. I don't know, students start so early, sometimes they take Algebra 1 in the 6th grade, the 7th grade. I don't know, maybe now students are taking Algebra 1 in the 5th grade. It's amazing how advanced our mathematical training has become. So again, what I want you to look at with these types of problems is just being flexible with notation, flexible with the symbolism that you have, be it in a math class, a physics class, an engineering class, some type of scientific type class where you're taking data and you have different symbols representing different quantities and things, just like we have with this interest formula. So again, not a very interesting problem, but a good technique problem for utilizing basic equation solving techniques. Okay, so what I want to do is do a few more equations. Well, not a few more, a lot more, because really when we think about algebra, ladies and gentlemen, we really do think about solving equations. If we're doing trig, we eventually have to solve trig equations. If we're doing conic sections, we have to solve equations to find vertices and foci and asymptotes. I mean, solving equations is what we spend most of our time doing. So before we actually do a formal statement of the quadratic formula, I want to just give you another example of solution by factoring. Okay, so what we want to do here is say solve in the real numbers. And I'll just say solve in R. Of course, you already know from college algebra that you can have imaginary zeros, but right now we're just focusing on the real ones. And if you find a discriminant that's less than 0, you'll know that the actual zeros will indeed be imaginary. So here's a good example. 4x squared minus 4x minus 15 equals 0. Now, when we think about an example like this, first off, you're thinking, okay, well, Professor Ron hasn't given us the quadratic formula, but I do know it from college algebra. So, you know, if I want to use it, I'll use it. And I would say fine with that. But in this particular example, I do want us to get better at factoring. Factoring in general, depending on what you're doing, if it's an AC lemma or whatever kind of factoring, working with exponents is an essential technique. And you don't get enough practice with it. That's why we will focus on factoring techniques. And there'll be times when you might be a little bit confounded by it, but that's okay. Better to have it now so that you'll be prepared for the calculus. So now, of course, we see that we have a quadratic equation in X. And the first thing we might want to do is just to assess whether or not the AC lemma works. Do we actually have rational zeros? Can we get the AC lemma to work? So let's go ahead and test that. Now, another thing I want you to notice is that all of these coefficients are relatively prime. Remember in the lemma where we had the A, B, C, greatest common divisor was 1? That mainly talks about a polynomial being primitive. That's a more sophisticated way of discussing a polynomial having being primitive. But really what it turns out to be is a time saver. So if we have extra stuff here, even if we're just factoring, it's good to remove that common factor to make the numbers smaller. And notice here, these are all relatively prime, so we're good. So let's look at AC. So this will give us a 4 times the negative 15. Now, of course, when we check this, we see the sum here is negative 11. And well, you know, that's not what we need. The equation is telling us that we need a negative 4, but we can actually rewrite this in a way that will allow us to get where we want to go. So first, what I'm going to do is just write 2 times 2, and then a negative 5, in this case, times a 3. Just do a prime factorization. You know the response is negative 60, so now you're already thinking what two numbers will work. And clearly that will be a negative 10 and a 6. So with the prime factorization, we can actually combine factors to get the z and w that we need. And so now we have a negative 10, 2 times the negative 5. And then, of course, we have the 2 times the 3, which is a 6. But then when we test with the AC lemma, we see that the sum of these two numbers is indeed negative 4. So if you like, you could call this the Z and the W. Not that you even have to do that, but that's from the statement of the theorem. And so we would have a check there. So now we would know that this polynomial can be factored in the integers. That is, the zeros here will definitely be rational. And that's an if and only if, ladies and gentlemen. Some students say, well, I'll just check the discriminant. If it's a perfect square, I'm good to go. That's another way to look at it. But it's always nice to have different ways to determine whether or not we can actually factor a particular polynomial in the integers that starts out as a quadratic integer polynomial. So now we can rewrite the middle term. So let's do that. So we have equivalently 4x squared minus 10x plus 6x minus 15. Just like we were doing for the last class. And now we can factor by grouping. Notice here we have a common factor of 2x in both of these terms. So this leaves behind a 2x. And here we have minus a 5. And now, of course, here when we look at these terms, we have a 3 that is common to both, which will leave a 2x minus a 5. So again, we always know that our work is correct when we get a common factor. Again, don't worry if there's a little slip up. You can always check your work and go back and make any corrections that may, or fix any mistakes that may occur along the way. That's just part of doing mathematics. And it's also called being human. So now we have common factor of 2x minus 5. So we have 2x minus 5. And then we have 2x plus a 3. So if we were just doing a standard problem just to factor this equation, we'd be done here. This would be a factorization, at least for two first-degree integer polynomials. And then, of course, we could be more clever and do the complete linearization, which we'll review later in the class. But at this point, to solve this, we can now use the zero product. So use, again, we do this without thinking about it, use zero product. So we can set each factor to zero. So equivalently, 2x minus 5 equals 0, or 2x plus 3 equals 0. So now, of course, we can transpose the 5. So this gives us a 2x equals 5. So x will equal 5 halves. Or we can transpose the 3, subtract 3 from both sides, 2x equals negative 3, and then divide by 2, x is negative 3 halves. Now, of course, you can use less steps here, but I just want to make sure that as we work through these types of equations that everybody's on the same page. How many steps you like to include in what I actually ask you to do for your test as far as written work, it'll just need to be clear to me that you have an understanding. And please resist the temptation to use online computer algebra systems. Ladies and gentlemen, that's not going to help you get where you want to go. And it will actually make you worse at what you're doing. So please be honorable in your work and work out your problems completely by pencil and paper so that you maintain the appropriate skills. Just again, I will always work problems as I'm doing here. And then on occasion, we may use our Google calculator to get a nice calculus approximation when WebAssign requires it. Because at this point, we don't even really know why our calculator works. It actually works because of calculus. But right now, you don't know that. So at this point, when we look at this, we see all we did was factor here. We didn't introduce any extraneous zeros. So we have actually two real numbers for which this equation is solved. And so we do our WebAssign, and maybe we have our box, and we list our solutions separated by a comma. Remember, all solutions are given as exact. You could certainly write these in equivalent decimals as 2.5 or negative 1.5. That would certainly be a correct answer because they are exactly equivalent. But usually what I remind students to do is just write the exact fraction. But if you do use a decimal equivalent, make sure that it is indeed equivalent. For instance, if you had 1/3 and you put 0.3, that would of course be incorrect because 0.1/3 is a non-repeating, is a repeating decimal. And so that would not be equivalent. So to keep from making careless errors with exact responses, it's probably best just to go ahead and type the exact response as a fraction, okay? Now, so I think everybody's comfortable with this, but of course, life is not good to us in the sense that not all quadratic or not all equations in quadratic form actually factor into integer polynomials where we can get nice rational uh, solutions. And sometimes we can factor things nicely and we still have issues. Now, what I wanted to say here, there was an example that I was looking at that a student asked about. Remember, I gave you that nice, before I do the quadratic formula, I gave you that really neat way to factor fourth degree polynomials with the trick of creating a perfect square and then treating it as a difference of two squares. Well, I had a student ask about this particular problem from that WebAssign problem. And let me just write this down. Here's an example. And the question was, is that I can't get that technique to work, Professor Ron. And I'm thinking, what am I doing wrong? Okay, so here's what we had before. That is, we had a quadratic polynomial in x squared, and we were thinking about making part of it into a perfect square and then having a subtraction of another square, which would create the difference of two squares. But here's the student was thinking, well, I've got to make that technique work. But here's an example where you don't have to use the new technique because the AC lemma works. Notice since this is quadratic in x squared, we can simply treat this first as AC lemma. And then of course, if it didn't work, we could try something else. But notice this is easy. AC is just 1 times a negative 2. And of course, if we just transpose the negative, we have a 2 times a negative 1. And of course, this will work. Since the 2 plus the negative 1 equals 1, the coefficient of x squared. So we're thinking, wow, this is really simple. We can just have x squared. Well, you can kind of do this in your head, but let's just go ahead and work it out like we normally do. We have x to the fourth minus x squared plus 2x squared minus 2. So sometimes when you're doing a problem and a new technique has been introduced, it doesn't mean you have to use it. It may not even work. And in this case, it didn't. And I thought how interesting that we find a new technique and we feel like we have to use it. That's quite all right. That's human nature. Now, of course, we can factor by grouping. So we have x squared times x squared minus 1. And then, of course, here we can factor the 2, x squared minus 1. So now we have the common factor of x squared. Let me put my square there, x squared minus 1. Here, let me bring the light down just a little because I don't want it to get too light there on the end. So Ipivo, it does everything except make coffee, but I don't drink coffee, so I guess I'm okay. So now we have what, x squared plus 2 times x squared minus 1. Now, of course, this is just a difference of squares, and so we can go ahead and keep going. So we get x squared plus 2 x minus 1 times x plus 1. So here's a part of that problem that I introduced where you did not have to use the new technique. And again, of course, the technique is very limited. This is a very restrictive type of polynomial, but we'll take what we can get. The solution of polynomials is a theoretical monument in mathematics, and it is no easy job. I think that's why students in general don't like factoring, because they're thinking sometimes factoring doesn't work, and what am I going to do? Some of you may go on to do some more numerical analysis at the university where you use computer algorithms to actually approximate solutions to equations. And you'll learn about that in Calculus 1. A nice second order method is called Newton's method, which is actually very useful and very accurate. So again, there will always be ways to get good approximate solutions when exact solutions may be somewhat difficult to obtain. So I thought I would throw that in so you can see that new techniques are great, but don't forget the old ones. They're still very useful. Now, what is that elusive formula? For instance, if we're working on a problem and we can't get the AC lemma to work, or maybe we factor something, but then we've got quadratic factors where we can't use AC lemma. Well, do we have another recourse? And we certainly do. It's called the quadratic formula. So here's a theorem. And basically, I'll just entitle this quadratic formula. Again, we could assume that the A, B, and C are complex numbers, but in this class, we're really going to focus more on the A, B, C being real numbers where there's a possibility of imaginary zeros, but there's certainly nothing wrong with having imaginary coefficients for a polynomial, which I'll maybe say something about later on in the course. So for now, we'll just suppose that A, B, and C are real numbers. Again, not necessarily an integer polynomial, even though that's pretty much what we'll be dealing with in this class. And we'll just say where, in this case, A is non-zero. We certainly want to have an x squared term. Then, if we look at this quadratic equation, that is, we're using the same notation. I know it gets a little bit dry. Ax squared plus bx plus c equals 0. And we really use only one direction. We don't often check our solutions. We just go back and check our work. This will actually have a solution if and only if x has the following form. That is the opposite of the coefficient b plus or minus the square root of a term called the discriminant, which is b squared minus 4ac divided by 2a. So what we see with this particular result is that when we look at this, we're thinking, okay, maybe we start with this equation here and we try a technique, AC lemma, or we try a factoring technique, which we learned, and it moves us forward in the problem. Or we try the AC lemma with a quadratic in X, and we don't find a Z and a W. So what this particular formula is saying is that you can always solve the quadratic equation, or you can always solve the quadratic equation that has that form. That is, maybe it's like this, quadratic in x squared, or it may just be quadratic in x. But notice here, when we look at this particular problem here, we have a 0 of 1 and -1. And then, of course, here, these would be imaginary zeros, plus or minus square root 2 times the imaginary unit, which you probably remember from college algebra. So the idea is we are very grateful when we can actually solve equations using square root properties and factoring techniques, but unfortunately, that's not always the case. And for the quadratic equation in general, or equation in quadratic form, we have this very nice formula. Now, after quadratic or degree 2, we don't have the luxury of beautiful formulas that are usable. The quartic formula for third degree equations, and excuse me, the cubic, and then the fourth degree equations, quartic, and then the fifth degree quintic, they're not usable. And past degree 5, there is no formula. The idea is that if the formula is so complicated that we can't even utilize it, we find that not to be the best way to go. So just remember that when we actually are asked in this class to factor higher degree polynomials, there will be some way to get at the zeros, at least in a way that we have some level of comfort. And then without that, we're going to use some calculus, or for instance, in your Calculus 1 class, you'll be able to analyze polynomials using derivatives and figure out some things about them that we wouldn't necessarily have at our disposal in this class. So what I want to do is, before we actually utilize this formula, is go ahead and derive it so you can be remembering the technique of completing the square. That's a really important technique here. So for instance, we'll just say, well, why is this true? And just for ease of use, we will suppose, since A is non-zero, we're going to suppose that A is positive. That'll be without loss of generality. That WLOG, without loss of generality, because if it were negative, we could just multiply the equation by a -1 and make it positive. So we'll just go ahead and assume that we have this. So when we're taking the square root of a squared, we just get a, the absolute value of a, which will be a in this case, since a is positive. So again, if I ever use this again, that's exactly what I mean without loss of generality. We're not going to mess up the result by making this assumption. It's certainly justified. So now we say we've got what? AX squared plus BX plus C equals 0. So now the first thing we want to do is just to go ahead and isolate the X terms. If you want, you can put the C over here, or you can leave it on this side. Since we have an equation, we might as well take advantage of that. So first what we'll do is we'll factor the A from these two terms, and that'll give us an X squared plus B over A X, and I'll leave some space here, equals negative C, or the additive inverse of C. That's what the negative or the dash means. Now, the one thing that we do when we complete the square was what I actually did over here. We want a monic polynomial. When we say monic, what we mean is that the leading coefficient is 1. So monic corresponds to leading coefficient is 1. Leading coefficient is 1. And the beauty of that is that as we factor this A, we can see now that we have a leading coefficient there of 1. And that makes the completing square process much easier. And this is something you've done in college algebra, but I just want to review it now. And I want you to know how to do this. When you get to Cal 1 and especially in Cal 2, you do a lot of completing the square. And even when we study conic sections, we'll be completing the square, much to everybody's dismay, right? Okay, so now what is the technique? What we do in order to add a number to make a perfect square trinomial is we take half of the coefficient of X. So I'll do a little sidebar here. We're going to say B over A, and then we'll divide by 2. That'll be the first process. So divide by 2 and then square the result. So when we square this result, we get a B squared divided by 4A squared, just like that. Now, again, this is the technique that we use to complete the square. That is, this number, when added to these two terms, will form a perfect square trinomial. And so now we can move this red term over here and add B squared 4A squared. Now, I'm not doing everything on the same side of the equation, so I'll have to compensate for this. Now, when we look at this, we see that we've added this term and we're multiplying it by an A. So that's going to absorb one of the A's here. So we actually have added B squared over 4A to the left-hand side. So we need to do the same over here. So we'll have B squared over 4A. Just like that. So again, since we have an equation here, we have the luxury, we could add and subtract the same thing, or we can just balance the equations like we're in Algebra 1 or a chemistry class. So now we have basically added B squared over 4A here, because that absorbs one of the A's, and we've done the same thing here. So this equation is equivalent, okay? So now, like I said before, this becomes the perfect square trinomial. So we have A, and now we can do it. This follows the form that we had in our identities. This will be X plus B over 2a quantity squared. So that is the number that goes right here. And so now when we square this, we have the x squared, we have the b squared over 4a squared, and x times b over 2a times 2 gives us the middle term. So that perfect square identity that we reviewed the first day, we see at work right here. And so now you notice that we have taken the quadratic and we have completed the square. So now we have only one occurrence of the x. It's inside the umbrella of the square. And that's the luxury of completing the square. It simplifies the process. Now over here, well, we've done the hard part. Once we do this part, it's really simple. So the difficult part is the mnemonic and then adding the correct term to complete the square. That is to give us a perfect square trinomial. Now over here, if you like, since we like our formulas to be neat, let's just get a common denominator of 4a. So we'll do 4a, and then of course we'll have b squared. We'll write this term first, and then of course we need to multiply the negative c by 4a. So that'll be 4ac. Again, very simple and certainly probably very familiar to you. Now at this point, we're thinking, okay, we're almost ready to use the square root property, but we need to divide by a. And again, a is positive by our assumption. So we have x plus b divided by 2a quantity squared equals b squared minus 4ac divided by 4a squared. So again, when we multiply or divide by a, we have 4a times a, or 4a squared. So now we have something squared equals a real number. And so we can use what we call the square root property. So now applying the square root property, x plus b over 2a now equals plus or minus the square root of b squared minus 4ac divided by 4a squared. Now, of course, the denominator is a perfect square. We know what that is. That's going to give us 2a because, again, a is positive. And just remember, one of our alternative definitions of the absolute value of a is the principal square root of a squared. But in this case, if a is already positive, then its absolute value is just a. So we use that relationship often dealing with absolute value. So when we look at this, we don't really know much about the b squared minus 4ac. That could be a perfect square, but we don't know. So we can't simplify that any further. So we have x plus b over 2a will equal plus or minus the square root of b squared minus 4ac. And then, of course, downstairs, the square root of 4a squared will just give us 2a, as I've noted right here. So now we're thinking, okay, well, this is looking fine. All we have to do is subtract this term, put the two fractions together, and we're done. So equivalently, x will now be, again, we can write the minus b over 2a first. Again, we've noticed we have the same denominator, so we can write one fraction bar. So we have 2a. And then, of course, now we'll have the minus b, or the opposite of b. And then, of course, plus or minus the square root of b squared minus 4ac. And so now what we're seeing is that this formula is actually quite doable. Unfortunately, for the next degree, the derivation is extremely complicated, or at least much longer than this. And again, the result is somewhat hard to use. So we are happy with what we have, but maybe we just have to live with the fact that in general, solving equations can be an arduous task. So now what we see is that if we're working a problem in physics or mathematics and we find that we can't use Professor Ron's AC lemma, we don't have some nice factoring technique that's going to get us forward in the problem, we can always utilize the quadratic formula. And again, this will always work. It doesn't mean if you're running behind on a test and you go ahead and knock out the quadratic formula, fine, just remember to write an exact answer. The main thing is that this is always something you can use. And I don't want you to ever be discouraged from using it. But when we need to factor, we'll have to factor. Sometimes it's hard to run this backwards. It's probably easier to start out with the factoring method than to try to run this backwards. But when you're working a problem, you'll take what you can get. Now let's use this new formulation. So here's an example of a quadratic equation where maybe Professor Ron's AC lemma would not work. So we've got the following. We have an example. We have 10x squared minus 16x plus 5 equals 0. So again, 10x squared minus 16x plus 5 equals 0. Now, again, you might look at this and say, well, we could try AC lemma. And then if you did, you think, well, we have AC equals 10 times 5. Okay, and then of course, you know that you need a negative here. So you would have to impose two negatives to maintain the positive product so that you get a negative 16. But when we look at this particular thing, we have, if we factor this, we have a 2, we have a 5, and we have a 5. Well, when we look at these particular factors and all, you know, we could get a 10 and a 5, a 15. That would be fine. That's maybe somewhat close to 16, but no cigar. So we can't really manage these factors to get a negative 16. The best we could get would be a negative 15, and that does only works in horseshoes, right? So we'll just say that we'll just say does not work. So we do not expect, you know, maybe we do this and we just don't see a factoring and it turns out that we actually had a perfect square. Well, that's okay. No big deal. The idea is that here it appears that the zeros are not, in this case, rational. So we can say, all right, we're fine. Let's look at the discriminant. So before you use the quadratic formula, always look at the discriminant first. Go ahead and knock this out. Don't put everything in the formula and substitute the numbers. It's too simple to make careless mistakes. Go ahead and do this first and then move to the formula. So now we have a negative 16 squared minus 4 times a 10 times a 5. Now, sometimes the numbers are really simple here. These numbers are easy. Usually I like to factor things because factoring usually just makes everything so much easier than dealing with a bunch of numbers that are, you know, maybe not the most courteous, so to speak. But we know that the negative 16 squared, that's a perfect square. That's 256. And of course, this is just what, 20 times 10, that gives us a 200. So we don't even really need to worry about factoring here. This would just be a 256 minus a 200, which just gives us a 56. Now, of course, if we look at this, this is just an 8 times a 7. And then, of course, 4 is a perfect square. So this gives us 4 times 14. Okay. Now, when you look, okay, it came, oh, good. It came from the quadratic formula. Good, good, excellent, excellent. Thank you for answering that, Jesus. Yes, very good. So what let me just go back here to our formula. Remember, when we do use the quadratic formula, like I said before, this is the formula. But instead of just throwing everything into the formula, go ahead and look at the discriminant first, right here, right here. And just go ahead and give that a name, discriminant, discriminant. Okay, and I'll say more about that, discriminant. So that's exactly what we're looking at here. Now, notice this is a positive number. When we take square roots of positive numbers, that's a real result. So notice here, this is positive. So this will imply two distinct real zeros. Two distinct real zeros. So when you think about the discriminant, maybe the discriminant 0, then you just get one repeated 0 because the plus or minus 0, that's not going to give you two solutions. Or it could turn out that the discriminant were less than 0. And then, of course, you're taking the square root of a negative number, which is imaginary. So that's going to give you complex conjugate zeros, just like you did in college algebra. So what I'm saying is help yourself out by looking at the discriminant first. Get a handle on that number. Know what kinds of zeros you're going to get. For instance, maybe WebAssign says find all real zeros, and you do the discriminant and it's negative, then you say none. Or maybe, or they'll say if there are none, it'll say type do not exist or type empty set or whatever. The idea is if you look at the discriminant first, you do save yourself a little bit of time. Now notice when we take the square root, we've got the perfect square here, so that's going to help us out. So now this implies x, and notice what's important here. I'll go ahead and write this down. A is 10, B is negative 16, C is 5. That's exactly what I used here. And notice another thing that's very important. We have what we call the standard form. When we derive the formula, all the terms are on one side of the equation. So we don't want to have terms on either side of the equation if we're trying to figure out what A, B, and C are. It doesn't matter which side you use. You could put all of your non-zero terms on the right-hand side or the left-hand side. It's not going to change the answer. Just don't have a mixing and matching, so to speak. So now we have the opposite of B, which is 16 plus or minus. Now we have our discriminant, and of course the square root of 4 is 2. So this is 2 times the square root of 14 divided by 2a, 2 times 10. Now, of course, this is good, but it can be simplified. That is, we have a 2 in all of these. There's a 2 here and a 2 here, so we can absorb the 2. So this will be 8 plus or minus square root 14 divided by 10. Now, when we look at this, this is as good as we can get. Notice here that there are no other common factors that will be easy to remove. And notice that the square root of 14 is simplified in the sense that there are no perfect squares in 14. So what we want to see here is that when we don't have the utility of Professor Ron's AC lemma, we do have the utility of the quadratic formula. And now we're thinking, oh, I get it. Here are our two zeros, plus or minus. So we can say, like in WebAssign, we can list our zeros exactly. We'll use our little fraction bar, go over to the math palette where you've got your fraction, click on that, and then upstairs we'll type 8 plus square root 14. And then downstairs a 10, that will be our first zero. Usually they won't mind which one you put first. If they specify, they'll let you know. Then minus 8, or excuse me, comma, and then 8 minus square root 14 divided by 10. Now, the idea is that later on, we're going to talk more about this, but you can see that the leading coefficient here is 10. And so when we do a complete factorization, there'd be a 10 on the outside, and then we'd have an x minus this number and an x minus this number. I'll say more about that when we review a complete factorization. But right now we see that these are the two solutions, the two real zeros that we get by using the quadratic formula. And again, like I said before, quadratic equations are our friend. We know how to solve them. When we see something in quadratic form or a quadratic equation, we breathe a sigh of relief, because that's something that we thoroughly understand. Now, let's look at another example. And before we move on to that, here, what I want you to do is write the following little litmus test down. So for instance, we'll just say number 1. We're going to start with the quadratic equation. I want you to write this down so you have this in your notes. So we're going to say b squared minus 4ac, the discriminant is positive, just like we had here. And then we're going to write, what does this mean? Well, this implies 2 distinct real zeros. And again, what we're assuming here is that A, B, and C are real numbers. 2, it certainly could be the case using the properties of real numbers that we would get a 0. Because if you have a real number, you know, what could it be? It could be positive, it could be less than 0, or it could be 0. So this means 1 repeated real 0. And in this case, what is it? It will just be minus b over 2a, because the b squared minus 4ac part is 0. This part would just be the 0, so to speak. So this is where we have 1 repeated real 0. So you'd have, like, say, you know, x minus 2 quantity squared. It has multiplicity 2, okay? And then 3 would be, what's the other case? That is, the discriminant could be negative, less than 0. So this would imply 2 complex conjugate zeros. That is, imaginary. And remember, when we have imaginary zeros, they might have some kind of form like alpha plus beta times I. and then alpha minus beta times I, not to use the same letters that I've used up here. So remember, when we have two complex conjugate zeros, that's when we have a negative discriminant, and our zeros are indeed imaginary because they have the imaginary unit in them. And remember, they'll have this form. The conjugates, remember, alpha plus beta I, alpha minus beta I. So again, the quadratic formula gives us plenty of information. And we don't take it for granted. I mean, when you solve physics problems, differential equations and things, the quadratic equation theory comes up over and over, and it comes up as you solve particular types of differential equations in calculus. So we can't stress how important the quadratic equation is. And that's why you spend so much time studying it, because you really just can't get away from it. Okay, so let's look at a situation which I alluded to last class, but I just want to give you an idea of, okay, say we have another equation. Do we have to use quadratic formula? Can we factor? Let's see what it tells us to do. So again, make sure that you have these in your notes so you can have these as reference. I know you know this, but it may be a little bit rusty. So let's look at an example where we have some fractions. And let's just see what kind of solutions we can get. So here's an example. So we have 10 divided by x minus 12 divided by x minus 3 plus 4 equals 0. So 10 divided by x minus 12 divided by x minus 3 plus 4 equals 0. And the directions are to solve in R. Now, when you look at this, and this is an important problem, you're thinking, well, once we get a common denominator, that is, we clear the denominators, we're going to have a quadratic term. So we might think, okay, well, we'll try AC lemma. If the AC lemma doesn't work, might be the case that we get irrational zeros. Or maybe we don't get any because the discriminant is negative. But the main thing that I wanted to point out was a situation I talked about before. Notice we have a 10 here, a 12 here, and a 4. We've got a 2 that's common to all of these coefficients here, these terms, and that's just in the way. So the first thing I'm going to do to make the number smaller is to divide all the terms by 2. Get rid of that extra 2 that's just hanging out, that's a thorn in our side. You don't have to do it, but it'll make the number smaller. So first, we'll just say divide by 2. So this will be a 5 over x minus 6 over x minus 3 plus 2 equals 0. So again, 12 is 2 times 6. 10 is 2 times 5. And of course, 4 is 2 times 2. So when you divide by 2, you're left with these numbers. And these are smaller numbers, so why not? Now, of course, we want to clear denominators because we're interested in finding out if there are actually some solutions other than the problems that just create division by 0, like 0 and 3. We clearly know that would never work. So we need to move the action of the x's into the numerator to see if that reveals an actual solution to this equation. So what we want to do is do a least common denominator. Here, let me give a little space here so I have room to write it. So we can say LCD. Of course, we've got a 1 here, so that comes along for free, but we need an x, and we need an x minus 3. So that's our least common denominator. So now we can do symbolic computation. So multiply both sides of the equation by x times x minus 3. Do the same here, even though it's just a 0. We'll go ahead and write it out anyway. So as you learned in your college algebra class, and also when you took Algebra 2, you did the same thing. But now we can do symbolic computation. Notice the x's absorb here, and we're left with a 5 times x minus 3. Now when we look at this term, the x minus 3's absorb, and we're left with a negative 6 times an x. And then for the last one, nothing absorbs. We just have a 2, and we have times x minus 3. But if you like, we can just go ahead and write that out. That'll be 2 and multiply. That'll be an x squared minus a 3x. Go ahead and multiply the x times the x minus 3 here to get that. And then, of course, 0 times anything is 0. So to save us a little bit of time, since none of these absorbed, I just went ahead and multiplied x by x to get x squared and x times negative 3 to get negative 3x. And then, of course, hit both of those terms with a 2. So now we have an equation that's clearly quadratic. We've got a squared term. So let's combine terms, make it more simple. So we have 5x minus 15 minus 6x plus 2x squared minus 6x equals 0. So we're actually at a point where we've got an equation that seems a lot more reasonable than this one, much more reasonable. So now let's go ahead and check everything out. We've only got one squared term, so let's write that first, 2x squared. So if you like, just put a little check. We've taken care of that. And then now notice when we look for the x terms, here we have a negative x. When we say 5 minus 6, negative x minus a 6x, that's a negative 7x. So check, check, check. And now when we look at what's left, the only term here is a negative 15. And we've checked that off. So again, what we can see here is what we have here is an equivalent equation. That is, if this equation has a 0, it must also be a 0 of this equation. Now, what that also tells us is that we must avoid 0 and 3 because 0 and 3 would not make any sense in the original equation. So if those came up as values of x's, they would have to be discarded. So again, don't, oh, great, I found a value for x, but make sure it solves the original. So we have to avoid 0 and 3 for obvious reasons. Division by 0 is undefined. We don't know what that means. So that could never be a solution. So now when we look at this, we're thinking, okay, quadratic formula or Professor Ron's AC lemma. Let's try AC. 2 times the negative 15. Now, of course, if we look at the negative 15 and the 2, that's a negative 13. So let's go ahead and break it down a little bit more and see what we get. So negative 5 and then a 3. So we'll just write the negative 15 as a negative 5 times a 3. But we're seeing that this will actually give us something we can work with, because if we combine these two factors, then that'll give us a negative 10 plus a 3, which is actually a negative 7. So this will actually work with AC. So this will be negative 10 times a 3. And if you think that could be a Z and that could be a W, and then we've got Professor Ron's lemma. So we know that the zeros here will be rational. So now let's go ahead and finish it off. So let's work with the negative 10 and the 3. So 2x squared minus 10x plus 3x minus 15. Again, Professor Ron's lemma is easy, and it's easy to teach to your friends. If you have friends that struggle with factoring, help them with this. You can easily teach this. Students remember this, and it's easy for them to teach their friends. So now factor the 2x from both of these terms. So that will leave us with an x minus a 5. And then, of course, here we can factor a 3, the greatest common factor, and that, of course, leaves us with an x minus 5. Now, of course, with the factoring by grouping, we have the common factor x minus 5. So we have x minus 5 times 2x plus 3. So we found that even though we had to do a little bit more work to move from here to here, it was a good amount of work, which at least resulted in an equation that we knew how to solve. So now by the zero product, we can set each factor to 0. So we have x minus 5 equals 0, or 2x plus 3 equals 0. Well, the first one's easy. We just get x equal 5. And then, of course, if we subtract the 3 here and divide by 2, we get x equals negative 3/2. So now we have 5. Again, I just run to this because, again, neither of these turn out to be the bad numbers, 0 or 3. So this doesn't equal 0 or 3. Same here. So we can use both of these. Again, just remember that I'm not overlooking the important thing. I've mentioned 0 and 3 a million times already, and we did not hit either of those. So again, just remember, as you choose solutions for your equation, if you've done some algebraic manipulations, make sure that you have actual values of x that work. Sometimes we introduce extraneous zeros through squaring. Here all we did, we're multiplying by variable expressions. And so as we transform things, there is the possibility of introducing values of x that could possibly not solve the original. But again, it's very easy to check that. Make that check, peruse over here and say, okay, we didn't hit the 0, we didn't hit the 3, so we're good with these two values. Now, what I wanted to do was do a couple of examples that deal with types of equations that might be a little bit off the beaten path. Sometimes you're working equations that have radicals in them. Sometimes you work equations that have fractional exponents in them. And you're thinking, well, what do I do here? Well, you do whatever you can. Usually it means either squaring or applying a power to remove a radical, or it means utilizing some factoring techniques. So we're not overly proud that our techniques seem to be whatever is useful at the point. We just look at the equation and say, okay, well, here's an opportunity to move this problem forward. So let's look at an example. One I found from your book looks like this. So it's got some fractional powers in it that looks a little bit intimidating. So I want to show you how to work it. So x to the 1/2. Sometimes things are in quadratic form, and that's even better. But sometimes we have to factor in ways that don't seem to fit a general pattern. So let me write down or describe what I've written here. So we have x to the 1/2. This IPEVO document cam is the best. I really grabbed the brass ring when I found this. This is a very good tool for teaching. So we have x to the 1/2 minus 3 times x to the 1/3 equals 3 times x to the 1/6 minus 9. Now, And here's what the directions say: solve in the real numbers. Now, when you look at this, you're thinking, well, is it quadratic form? Maybe it's quadratic form. Maybe I get some common factors and I can rearrange things in factor. But the first thing we want to do to make this problem easy is to make sure that all these powers have the same denominator. And then we can figure out what we have. So first, let's get a common denominator of 6 in all of these fractional exponents. So we have x, so we have a 6, 2 into 6 is 3. So that's going to be an x to the 3 over 6. Let's go to the next one. Again, a common denominator of 6, 3 into 6 is 2. So that gives us 3x to the 2 6. Well, 6 is already there, so we don't have to do anything to that. 1/6. The common denominators in the fractional exponents help you to see the factoring that you can possibly do. Now, notice here, we have common factors. If we look here, we've got an x to the 2 6 here and an x to the 2 6 here. We're left behind x to the 1 6, but we can factor x to the 2 6 out of each of these terms on the left-hand side. So let's do that. So I'll just say now factor. First, we'll say common denominators. One thing I always tell students about math problems, try something. Don't just stare at it, and don't do something you know is incorrect, okay? If you get common denominators in these fractional powers, that's going to illuminate something for you, but don't make it up. Don't just do something you know is wrong, because that's not going to help you at all. So now notice we can factor. So we have x 2 over 6, and that leaves behind x 1 over 6. Again, remember when we add 2 plus 1, we get 3 over 6, so that's correct. Now what's left here? Just the minus 3, right? So now when we multiply this, we get the negative 3x to the 2 6. So this works. Remember when you multiply like bases, you add the powers. So 2 6 plus 1 6 is 3 over 6, which is exactly that. Now, what's the common factor over here, ladies and gentlemen? Well, we can see we've got a 3 here and a 3 there. And that's good because we're going to get the same factor here. So now we can factor the 3 out of each of these terms. All right. So this is like this isn't like, this is factoring by grouping. Because now when we look at this, we can shift everything to one side. We've got this common factor here, and then we can use zero product. So this is what I'm talking about. You might be in a science class and you end up with an equation like this. And it's like, well, it doesn't fit any pattern I've used recently, but let me see if I can factor. So factoring, even though students run away from factoring, factoring is an essential technique. And we see that it's going to bail us out of this problem. Whereas had we never thought about any of this, we'd just be staring at it. So now remove this to the other side and factor. So we have x to the 2 6 times x to the 1 6 minus 3. And now just subtract this, take this whole term over, minus 3x to the 1 6 minus 3 equals 0. So the idea here is now, again, just like we're doing Professor Ron's AC lemma, we're good to go. We've got the common factor to give us a product. So now we have x to the 1 6 minus 3 times x. Now we've got 2 6 here. We can just go ahead and write that as a 1/3. It doesn't matter anymore. This 1/3 minus 3, right? I mean, you can write it as a 2 6, but now when we solve it, we're just going to be cubing the 3, and we're going to be raising 3 to the third power, or excuse me, the 6th power. So now look where we started. When you think about what we've done here, look where we started and look where we are here. This is an easy problem. But when you consider what we had initially, it was just like the last problem. When you think about this, we look at this and say, but then we look at this and say, oh, that's a doable problem. So the same technique is involved. What we want to do is reduce the original equation to a form that we understand. What is it that we do in math? We look for patterns, pattern recognition, okay? If we don't understand the pattern, then we don't know how to move forward. So that's how you learn mathematics. It's learning a language, like you learn the English language, or you learn the French language, or you learn the Spanish language. You learn words, you learn how to put the words together. In math, we learn symbols, and we learn how to put the symbols together. So we have to recognize things to understand them. When you read words, how do you understand it? You recognize them. You recognize what the words mean and think, oh, I get this. Math is exactly the same. There's absolutely no difference. So when we add new ideas to our mathematical vocabulary, we get better. Just like when you add new words to your Spanish vocabulary or your English vocabulary, you have better ways to communicate. So it's the same thing. We just have to tell ourselves that that's all we're doing, even though we wish it could be easier. Now, by the zero product, we have x to the 1/6 minus 3 equals 0, or x to the 1/3 minus 3 equals 0. So now what we can do, this is kind of going backwards. We're just raising the powers. So now we have x to the 1/6 equals 3, or x to the 1/3 equals 3. So now in order to find x here, we have to raise each side to the 6th power. So this is going to be x equals 3 to the 6th. But that's just going to be what? 27 times 27. And that's something that we know. That's actually 729. And I can show you how to compute that. I'll give you a little trick to compute that. And then I had something that I wanted to say here. Notice x, now when we cube both sides, will just be 3 cubed. So x equals 27. Now, let me show you a little trick that you may think is a little bit silly, but notice here, 27, we could think of something like this. We could say, okay, 27 equals 30, or squared, equals 30 minus 3 squared, right? Okay. And so then you're thinking, all right, well, this equals 3 times 10 minus 1. Okay, so now if 27 equals 30 minus 3, and then I can factor the 3, so that'll be 3 times 10 minus 1. Okay, that's still 27. Now I square it. So this is going to be what? In this case, 9. And here, this is going to be 9 squared. That's an 81. And that's easily 729. So that's a simple way to compute by using symbolic computation. You're thinking, that's crazy, Professor Ron. I wouldn't do it that way. But here's what I'm trying to show you. You can let the algebra help you work with numbers. Numbers and letters, they're all the same. They all behave the same. They represent numbers. And so we treat them as mathematical objects. So now when we look at this, we can see, and maybe had you just stared at this problem for 3 or 4 minutes, you probably would have figured out these solutions. But now we have what? 729, comma, 27. So the idea here is when you look at the numbers and the threes and the nines, you're thinking, well, I'm sure there's got to be a power of 3 in the solution because I've got 1/2, 1/3, 1/6. But you know, you want to make sure you get all of them. So here's a situation, ladies and gentlemen, where factoring technique is essential. That is, we don't look at this as maybe a particular pattern like a quadratic. We look at this and say, well, what can we do? Common denominators, factor, use the common denominators to see a simple factoring, and then work with what we have. So here's what I want to impress upon you. You might be working a physics problem or a calculus problem, and the only thing that gets you from point A to point B, the end of the problem, is clever factoring. So factoring and working with expressions is something that we want to continue to practice in this class. And even though at times it doesn't seem like we're going anywhere with it, it will pay off later down the road. Now, there's another equation that's similar to this I wanted to give you some practice with. And it goes like this. We'll do some word problems next class. You get to do some more of the time, rate, distance, and things like that. I know you enjoy those. Maybe you don't, but that'll be a blast from the past. So here's an example. So we have, I wanted to throw some radicals in. We have the radical of 11 minus x squared minus 2 divided by the same radical, 11 minus x squared equals 1. And we want to solve in R. I mean, in some cases you might get a quadratic form, and in other cases you're thinking, well, how am I going to get rid of these radicals? And is this going to give me a form that I actually already understand? Well, the reason I thought this one was good is because you're thinking, well, I've got 2 radicals, I need to square. Well, we don't, one of the radicals is in the denominator, and this actually has a quadratic form if we look at it in terms of a substitution. Now, I'm not a big fan of substitution in college algebra. I like working with the variables that we have, but there are instances when a substitution can help clarify, and this is indeed one of them. I only am a supporter of the substitution when it moves the problem forward to a point that actually helps you to solve it and not create just unnecessary clutter. Clutter in a problem is a waste of time, but a substitution that helps you think correctly is a bonus. So what I'm going to think here is, since we have this repetition of the radical, is here's what I'm going to do. I'm going to let z, I'll just use the letter z. Now, when I do a z, I'll put a little cross in it like that so it doesn't look like a 2. So I'm going to let z be the square root of 11 minus x squared. And of course, if you stare at this long enough, you can figure out an answer. So there's nothing wrong with that. We just want to make sure that we find all of them. So then, what kind of form is this going to have? Well, this will be z. You could call it x, but since we're already using an x, I use z instead. Minus 2 divided by z equals 1. Now, if you look at this, this is exactly like this problem here, clearing the denominators. So we now have a problem that looks like this. Okay, so when you look at this, you're thinking, well, I can solve this if I can clear the denominators and then see what happens. Obviously, 0 is not going to work for z. That would have to be something that would never work. But the least common denominator here is z. So we can just say LCD is z. So since I wrote it, let me write it again after this, since that's kind of something new. So I'll have z minus 2 over z equals 1. So let's clear the denominator, so to speak. This is just one technique to solve this. I thought it was interesting. So now again, let's write an equivalent equation by symbolic computation. Z times z is z squared. And then of course here, what happens to the z's? They absorb and we're left with what? Minus 2. Again, the 2's look like 2's. There's no cross in them, so don't think of those as z's. And then of course, what's 1 times z? That's just z. And you're thinking, hallelujah, this is so much easier, Professor Ron. So now we have z squared minus z minus 2 equals 0. So I thought these were interesting equations that do come up in mathematics and science, but maybe don't come up all the time when you're just thinking about math in general. But now you can see AC works, because if we do AC, this is just 1 times the negative 2, and that's a go, because 1 plus negative 2 equals negative 1. So now this gives us z squared plus z minus 2z minus 2. Of course, you could factor this in your head, but I just want to go ahead and use the technique I've taught you. So this will give us z times z plus 1 plus negative 2 times z plus 1 equals 0. So now we have z minus 2, z plus 1. Now, when you look at this, you're thinking, wow, how simple is this? We got a quadratic equation that's equivalent and 0 product. I mean, all the easy stuff that we like to use. Well, it's easy as if we can get to that point. And so now we know what z is. It's a principal square root, but here's where the substitution is valuable, because the square root is non-negative. The principal square root cannot be less than 0. So that's going to help us discard some things. So now by 0 product, we have z equals 2 or z equals negative 1. But now here, notice that's going to mean that a principal square root is less than 0. So this will be discard. Discard. Let me put the S first. Discard. Since the square root of 11 minus x squared, which is z, is non-negative. So we're done with that part. Now this one actually does make sense. So you're seeing that all we're doing is using properties that you've been using from day one in general math. No reason to forget them. And so now we have the square root of 11 minus x squared equals 2. Now you're thinking, okay, well, this problem just gives us a little bit of everything. So now in order to solve for x, we just need to square both sides to eliminate the radical. So let's square both sides. So we have 11 minus x squared equals 2 squared, which is 4. So square. And now bring everything over. X squared equals 7. So subtract 4 from 11, transpose the x squared term, and now use square root property. If and only if x equals plus or minus the square root of 7. And now when you look at this, you're thinking, I could have stared at this a long time and figured this out, because when you square this, you'll get 11 minus 7 is 4, square root of 4 is 2, and then 2 minus 1, again, the same thing, equals 1, ding, ding. And then, of course, the negative works too. So like I said before, if you stare at these long enough, you can probably figure out a solution, but maybe you don't have time to do that. You've got to work it out and move to the next problem. So now we can see that we have two bona fide solutions here. That is square root 7, the negative square root 7. So I thought this was an interesting example where we see that we have a form which is really a fractional equation, where a substitution actually turns out to be very useful here, because instead of adding clutter, it actually helps us. The idea is that a substitution, ladies and gentlemen, must move the problem forward. It must make it easier to understand. And so now when we develop a very simple quadratic, we can now utilize what we know about square roots and then square to eliminate the radical, and then we're done. So I thought this was an interesting example, because when it comes to lots of equations, they don't necessarily fit a particular pattern. If we work with it, we can discern a pattern that we understand. So once we get to here, we know what to do. Once we get to here, at this point, we know what to do. Once we get to here, we know what to do. So we're using all of these nice college algebra techniques in concert, so to speak. Sometimes when you work a problem, you use very many techniques in one problem to get to a solution set. So I thought this was an interesting example. Now, I want to look at a couple of models. This is going to take us into our work for our next class. So before I mention that, I just want to give you just a little extra on absolute value. We're going to use absolute value a lot in this class, but I just want to remind you. So I'll just say recall. I had a couple of examples here that I wanted to mention. Recall that when we have real numbers, later on when you do complex analysis, you'll extend the absolute value to that. But for now, we'll start with real numbers. One of our major results, which I've already talked about, is we define the principal square root of x squared to be the absolute value of x. So you're thinking, well, what does that mean? You've got these fancy symbols and more symbols. So this is what we refer to as the absolute value of x. And this is a very convenient way of writing it. That we saw this in the derivation of the quadratic formula. And since we assumed that a was positive, when we actually take its absolute value, we know it's just plain old a. But why is that? Well, here's the second part of this definition. In general, how do we think of the absolute value if we're not looking at it as the square root of x squared? Well, we can think of it as a function in two pieces. So, and this is what we use a lot in calculus. We can say, well, this will be x when x is non-negative. So if we have a real number x, we say its absolute value is x when x is non-negative. And then we say its absolute value is the additive inverse of x when x is less than 0. Again, you know this very well, at least intuitively, but now we need to realize that when we actually have a dash in front of something, that means additive inverse. It doesn't necessarily mean that the dash x is less than 0. It just means that in this case, if x in this case is actually less than 0, the additive inverse of x will be positive, okay? Because what is the additive inverse of x? It is the number we add to x to get 0. What do we add to 2 to get 0? -2. What do we add to -3 to get 0? 3. So the idea is that we want to extend our understanding of absolute value in a way that takes us to the next level and not just, take its positive kind of thing. Because again, when we deal with it in terms of symbols, it makes it a little bit more complicated. So we can say by definition, the absolute value of x is always non-negative, always. And so when you graph it, you get that famous V shape. You basically get two lines, y equal x and y equal the additive inverse of x, which gives you that V shape, okay? So again, this is like a problem you use when you do the function transformations. Now, one small lemma I'm going to add to this that you're going to use in section 5 of chapter 1 is the absolute value equation. So here's a lemma. So we can say, suppose that C is a positive number. And we'll add to this later with inequalities. So if we have some positive number C, then we would say that the absolute value of x, or some expression in x, like a we used before, equals C, if and only if x equals C, or x equals the additive inverse of C. So when you think about this absolute value extends the number of solutions. So the idea here is that just thinking about this, you're like, well, of course, if x is what non-negative, then x equals C. And then, of course, if the value of x were less than 0, then its absolute value would be the additive inverse of x. And then when you solve for x, you get the additive inverse of C. So the key here is that absolute value often will extend the number of solutions. So here's a simple example of this. Say we have 3t minus 2 equals 5. Again, a very simple equation that we can actually solve using this lemma. Again, if it's more complicated, we have to work a little bit harder, but I wanted you to be able to negotiate some simple absolute value equalities, and then we'll do more as we get more refined. So now when we look at this, we're thinking, okay, we have an expression here in T that's isolated, and we have a value of C here, which is 5. And so what we have here is this hypothesis of the theorem. So this we have here. That is, x has been replaced with 3t minus 2, and c has been replaced with 5. So we can take this side and write it as this side. So by lemma, by lemma, we have 3t minus 2 equals 5, or 3t minus 2 equals the additive inverse of 5. Okay? So again, we're extending the number of solutions with the absolute value. Some, in some cases we may not, but we know from the definition of absolute value that we have at least one of these when this is true. Okay? So now we can easily solve. So 3t, add 2 to both sides is 7. So divide by 3. Again, very simple based on what we've been doing with all the complicated maneuvers we had to do in the last two problems. And here we have 3t. So we're going to add 2 to negative 5. That gives us negative 3. And divide by 3, t is negative 1. So now when we look at this absolute value equation, we have zeros, 7/3, and negative 1. So again, you might be thinking, do we get a lot of occurrences of the absolute value equality? Not as much. What we're going to end up seeing more in calculus is the conjunction, which we're going to talk about soon, which will extend this lemma to two more pieces, the conjunction and the disjunction. But I didn't want you to run into this and say, well, what's this absolute value mean? The idea is that you can get clever about this and just remember that at least one of these would be true. And of course, if C here does not satisfy this, then it wouldn't make any sense. For instance, if we had the number here is -5, then of course there'd be no solution. And that wouldn't be the lemma. That would just be the fact that the definition requires this to be the truth. So often, a lot of times, students will make mistakes dealing with absolute value when they ignore the definition. So when it comes to doing pre-cal, we like to kind of start to rebuild how we think about some of these functions. And even though this is very simple at this point, it's going to help you start to think about why the absolute value is so important. And it does help us to rewrite inequalities in a convenient, symmetric way that we find very useful when we do the calculus. And I'll certainly say much more about that. Now, what I want you to think about with what's coming up, if I'm going to go ahead and post some new sections with the WebAssign that will cover items that we'll do next week. But what I want you to do is to spend some time working on these types of problems. That is, work in section 3, 4, and 5, honing your skills, so to speak. And so just remember that the homework for this week and the quiz will be due next week, so you get a cushion of time. But like I said, I'll go ahead and post some new sections. And if you want to go ahead and look at those and work ahead, you can certainly do that. But I want to give you enough time to come to conference hours and ask questions and to be able to think about what you're doing, to give you time to assimilate. And that's the main thing. But remember this, it's very important to meet the deadlines, and the deadlines will always be clearly delineated on WebAssign. One good thing about mathematics that's extremely important is that we stay current with the work. Do not get behind in math. Do not get behind in math ever. It is just one of those classes that is just unrelenting. There's always something new, and you're having to work with what you already know and then build in new concepts. So allow yourself flexibility, but don't allow yourself to get behind, because math, again, like I say, it's unforgiving. It never lets you sleep, so to speak. Now, in closing, I just want to give you an example to think about, and I'm going to show you how to do this next class. And I'll just go ahead and cover this up. Here's an example. I just wrote this out. This is in models. Now, I want you to think about this in terms of symbolic computation. We're going to be doing time, rate, distance, fraction of work, and mixture problems, which will be the main focus of the models that we do in your review from college algebra. But I thought this was an interesting problem that I included in the WebAssign. And let me just go ahead and state this to you. It says Ben invests $4,000 at 4% annual interest. And then it says how much additional money must be invested at 5.5% annual interest to ensure that the interest received is 4.5% of the total amount invested. Now, you might look at that and say, oh, I can do that with some decimals and it's no problem, Professor Ron, I can figure this out. But here's what I want you to do. I want you to create symbolic calculation here. First, if you have 5.5%, I want you to use fractions to represent the percentages. So remember, this would just be the same as 11/2% if you wrote 5.5 as a improper fraction. And then of course, the definition of percent, you divide by 100. So that's what this equals. So what I want you to do is to write all these percentages with the same denominator, so to speak, and then clear your fractions like we've done several times today, and then create an equation that's easy to work with. What I want to try to help train you to do in this class is to rethink about how you solve equations in a way that makes you more efficient. So again, if you don't do that, that's okay. But like I said before, I will post some of the new sections up so that you can go ahead and look at those for next week. If you get bored with what you're doing now, you may have plenty to do. And today I've got several conference hour sessions. So I will get busy sending out emails for those sessions. And like I say, you will always have an email in your inbox which will cover a session that I'm doing that day, so it will be available to you. The main thing is that when you have questions, I want you to know that I'm available. But there may be days when you're caught up and you don't have any questions. So students always say, am I required to attend? And the answer is no. You are only required to attend if you have questions. And then of course, if you would prefer to send me a WebAssign message or you'd prefer to send me an email, the WebAssign message is good. I can get back with you with some hints. Every student is different. And I want you to feel comfortable to be able to talk with me about the problems that you're working on. I just remember last term, the Zoom conference hours were very popular, and lots of times we have several students and we just go in succession. But if your colleague asks a question, it's probably something that you can benefit from. Or maybe you've already done it and you can share some of your expertise. So look forward to some emails today for our sessions that I'll be holding. I'll actually have one in the evening too, if that'll be more convenient. And so I appreciate your attendance today. Thanks for your attention with these problems. I wish you well as you start your studying. And then again, of course, if I don't see you today, I'll have a conference hour session on Friday. So I look forward to hearing from you with your emails and your messages, and also with the conference hours. So everyone have a great day, and I'll see you later on today.